Hi everyone, my name is Ying Li, and today my topic is Open Shop Scheduling is a way of intelligent algorithms. Let's have a look what will be covered for this presentation. First, I will do an introduction for Open Shop Scheduling problem. Then I will introduce four different intelligent algorithms, which are genetic algorithm, particle swarm optimization, QQ search algorithm, and anti-cloning optimization, and then following with a conclusion. Introduction. Scheduling is a service which can ensure that the factory can produce products effectively, and the open shop scheduling problem is one of the main branches of the scheduling problem. The open shop scheduling problem, OSSP, has no restrictions respective to the processing route of each shop during the production process, and can be regarded as a generalization of the shop scheduling problem, JSSP. In OSSP, the solution is represented by two processing orders, which are operations within jobs and operations on machines, while the solution of the JSSP has only one order about operations on machines. In practice, OSSP has several common performance indicators, which are minimizing the mix bin, minimizing the sum of completion time of all jobs, and minimizing the weighted of completion times of all jobs. In this study, the first indicator is considered. In order to solve the NP-hard OSSP, intelligent algorithms were proposed to get better performance. Intelligent algorithms mimic natural biological evolution and the social behavior of species to achieve the best result. Besides, it uses random numbers to overcome the local optima defect. This method can achieve a reliable solution with an acceptable computing power and time. Many different intelligent algorithms have been introduced for OSSP. Genetic algorithm was used to solve the OSSP, and the improved genetic algorithm was with crossover and mutation were specially designed. An efficient local search algorithm based on taboo search was developed, and the hybrid mode combined taboo search and genetic algorithm was also proposed. In addition, some researchers adopted simulated annealing algorithm to solve the OSSP, and cloning optimization was introduced into the OSSP. In general, intelligent algorithms in the OSSP are still under development. In this section, several intelligent algorithms for the OSSP will be introduced. The algorithms varies from traditional algorithms like genetic algorithm to newly released ones like QQ search algorithm. In all of the algorithms proposed, the solutions are presented in the format of sequence. In the sequence, each number represents the label of one operation. The former operation in the sequence operates first, and when the machine is empty, the later starts operating. A simple example consisting of 4 jobs and 4 machines will be shown next page. The array here is an example of sequence, and table here is the processing time of each operation. The first number is 9, which means the third job is processed on the first machine first. Then the number 14 appears, which means the fourth job is arranged on the second machine next. Since the two operations require different machines, they can be operated at the same time, which is time 0 in this example. After that, the number 2 appears, which means the first job is placed behind the fourth job on the second machine. The rest is scheduled based on that rule. Therefore, the Gantt chart is showing in the figure here, where Pij stands that the time required to process the j's job on the ice machine. Genetic algorithm. Genetic algorithm is one of the oldest algorithms. In genetic algorithm for OSSP, each chromosome can be represented by a sequence which indicates a possible solution. The whole process can be realized as follows. First, random results are generated to be chromosomes of the first generation. Then in each generation, selection, crossover, and mutation are applied to the chromosome population. After that, elite strategy is performed to the population to further ensure that the best chromosome is survived to achieve better result. Finally, the population is updated and another generation is generated. Some important parts in genetic algorithm are shown in the following. In selection process, candidates of the next generation are selected based on the score of the chromosomes, which is just the reciprocal of maximum indicated by the sequence of the chromosome. The bigger score means better result, and the chromosome is more likely to be selected. In the algorithm, for each chromosome in the next generation, half of the chromosomes in the previous population are chosen. Then the chromosome having biggest score will be selected to the candidate of the next generation, and then repeat the process until all candidates are selected. In crossover process, two candidates are randomly selected at a given probability, and the two sequences are put together and generate another two different chromosomes. The numbers of first and second chromosome are visited one by one. When visiting a number, the result of first chromosome is visited, and if the number is not in the current result of first chromosome, the number will be added to the first chromosome. If not, the number will be added to the second chromosome. A simple example is shown in the figure on the left. In mutation process, a new chromosome is generated by one candidate, which is randomly selected at a given probability. In this process, a subsequence is randomly chosen. Then the numbers in the subsequence are swapped from left to right. A simple example is shown in the figure on the right. After mutation, one last step is to apply the elite strategy. If the best chromosome of the new population is worse than the best chromosome of the old population, then the worst chromosome of the new population is replaced by the best chromosome of the old population. Practical swarm optimization. In PSO for the OSSP, the dimension of the particle position is equal to the length of the result sequence. The order of the dimensions of the position is the result sequence. Given that the PSO is suitable for continuous problems and OSSP is a discrete problem, the process is shown below. All the particles are randomly generated, and best solutions of each particle and the whole population are calculated at first. Then the population is updated by using the following formula in metric form. In the two formulas, V is the velocity of the particle. W is the weight of current velocity, which is given by people. X is the position. R1 and R2 are two random numbers to get more random result. C1 and C2 are two given factors to control relationship between local search and global search. XGB is the global optima and XIB is the optima of each particle. During the update of population, the range of position and velocity are controlled so that velocity and position will not be too large or too small. After that, the optima of population and particle will be updated by sorting the position of each particle and getting an order as the sequence which represent OSSP's result. Then the process continues until the termination condition is reached and the best result is output. QQ search algorithm. QQ search algorithm is a relatively new algorithm. In CS for the OSSP, the position of needs are presented similar to the results in PSO. The position has dimension of length of the sequence, and the order is the result. First, needs are generated randomly, and fitness is calculated. Then, for each generation, a cuckoo bird is flying based on levy flight, following the first formula below. In this formula, alpha is the step length and lambda is the levy coefficient. A new result is generated while a nest is randomly chosen. If the new result is better than the nest, cuckoo bird's egg successfully replaces egg in the nest and the position of egg changes to the new result. After that, nests are abandoned at a given probability and the new needs are generated following the second formula here. In the formula, C is a random number and PA is a abandoned probability given. Ni minus Nt means the distance between two needs so that birds move to another position hiding to another nest. The position of new needs is controlled in the search space and better needs are kept to improve the population. Finally, the process is repeated and the best result is output. And cloning optimization. And cloning optimization is also a new algorithm, which is an agent-based algorithm. In ACO for the OSSP, the max-min end system is introduced. The result sequence is the route ends move through, except that ends cannot move to a repeated position, which is controlled by a taboo list. Therefore, the process is similar to the one for traveling salesman problem. At first, the pheromone in all routes are set to the biggest number. In each ends move, the end has either random move or move according to pheromone at the probability relative to pheromone's density. In the formula, P is the pheromone on all available routes whose destination number has not been visited. If the ant moves randomly, it will move to a random number not being visited. If the ant moves according to pheromone, the probability of moving through each route is the pheromone on the route over the sum of all pheromones, which is Pi equals to Pi divided by the sum of P. Besides, a taboo table is used to record the available route in ants move. After one round of ant moving, the pheromone on every route is updated. The pheromone is evaporated at the ratio, and then the best ant whose route has the best solution in the whole process will leave more pheromones at the rate of the score of the solution. Then the pheromone on every route is controlled in a specific range, and finally, to avoid local optima after the best route remains the same for a certain generation, the pheromone on other routes will increase to jump out of local optima. The process is repeated until a final solution is output. In conclusion, This study deals with the open shop scheduling problems in order to overcome the limitation of the MILP method in solving open shop scheduling problems. Intelligent algorithms such as genetic algorithm, particle swarm optimization, cuckoo search algorithm, and ant colony optimization are introduced using a sequence to determine the processing order of all operations. In addition, each intelligent algorithm has been modified to fit for the OSSP. Due to the randomness and swarm intelligence, the intelligent algorithms can deal with large-scale problems which cannot be solved by the MILP method. The ant colony optimization algorithm can have best solution on tiny scale problems like 4 machines and 4 jobs, but when it comes to large problems like 10 machines and 10 jobs, it can only achieve poor solutions. Therefore, it may not fit for the specific problem. Meanwhile, cuckoo search algorithm may be not good at solving tiny scale problems, but it performs well on large scale problems and gets the best solution among the proposed 4 algorithms due to the levy flight and other features. Okay, so that's all for my presentation today. Thank you, everyone.